So today, we're going to be reviewing the structure of an atom for physical science. Alright, and so as many of you know, atoms make up everything in our world. However, we can't see them with the naked eye. They're microscopic. We can only see them with really powerful microscopes. But, since they make up everything, we know that they are the smallest unit of matter. But atoms are even made of smaller particles. And we call these subatomic particles. And we have a total of 3 subatomic particles. Now, these subatomic particles are in certain parts of the atom. We have 2 of them in a part of the atom called the nucleus. And you can think of the nucleus like being in the middle of the atom. Inside the nucleus, we have 2 particles, the proton and the neutron. Outside of the nucleus, we have our 3rd particle, called the electron. Now, each of these particles has a charge. The proton is positive, the neutron is neutral, and the electron is negative. That's why we can write out the symbols of each of these atoms like so. The proton is a P with a plus, the neutron is an N with a 0, and the electron is an E with a minus. So going back to think about our nucleus, if we have 2 particles, a positive one and a neutral one, then that must mean that the nucleus is overall positively charged. Outside of the nucleus, if our only particle is one negative one, then we know that the area outside the nucleus must be negatively charged. So let's go into a bit more detail about these electrons. So the electrons are not just outside the nucleus, they orbit the nucleus. And they are very, very small compared to the proton and the neutron. They're about 1/2000th the size of these particles. So they do not contribute to the mass of the atom. That doesn't really be affected by the electrons. What they do is give the atom size. And remember that they have a -1 charge. So talking about how they orbit the nucleus, in physical science, we like to say that they're at specific distances from the nucleus called energy levels. You go a bit more into this in chemistry, but right now we can say that around the nucleus we have these rings. And each of these rings is an energy level. What we have drawn out right now is 2 energy levels. But really we have more than that. We have 3, 4, 5, 6. We have a lot more energy levels possible. The thing about these energy levels is that they each have a maximum number of electrons that they can support. The first energy level can support 2, while the second can support 8. Okay, and so let's remember charges. Like charges attract. So the nucleus is positively charged. And the first energy level is full of electrons, which are negatively charged. So they're going to be attracted to each other. That's why we say that closer energy levels have less energy. Because it does not take much energy to hold them close together, because they want to be close together. However, the further away we get, the more energy we need for these charges to attract. So that's why the further out we get, the more energy the energy levels have. Alright? And so, now we can talk about the outermost energy level. And this is a very important energy level, because this energy level is what holds what we call valence electrons. And so atoms follow a rule called the octet rule. And this rule is very important because atoms want 8 valence electrons. This is how they become stable. Okay? And so what happens when atoms don't have 8 valence electrons? Because obviously not all of them do. Well, they partake in chemical reactions. So that means that our valence electrons are going to either be shared or transferred. So when atoms react, it's actually the valence electrons that do the reacting. And these valence electrons are either shared or transferred in order for the atom to fulfill the octet rule. So think of the octet rule as what the atom needs to be happy. And so having 8 valence electrons will make the atom happy, and it will do what it needs to be able to get 8. So talking about the other 2 particles, we have the neutron. Now, because the neutron is neutrally charged, it doesn't really do a lot. But what it does is that it gives the atom stability. And this is important because we can't have an atom that's all protons. We need the neutron in order for it to be a functional atom, for it to be stable. And what they also do is contribute to the mass. So the mass of the atom is in the nucleus, which is composed of the proton and the neutron. And remember that in most atoms, the number of protons is equal to the number of neutrons, and they have a mass of 1 atomic mass unit. Alright? So for the proton, we have the same mass, 1 atomic mass unit, but this time we have a positive charge. Alright? We also know that if atoms are overall neutral, then the number of protons must equal the number of electrons. They also contribute to the mass of the nucleus. Now, if we've looked at the periodic table before, we know that we have a certain way of representing elements. We have a number at the top, then a letter, then a larger number at the bottom. Okay, so the number at the top is called the atomic number, and that is the number of protons, all right? Okay, and so the number of protons are what actually give the atom its identity. So for example, 6 protons makes up carbon, and 7 make up nitrogen. 1 proton would be hydrogen. So the number of protons affects what element it is. Now the atomic mass is the number of protons plus the number of neutrons. So if we wanted to find out the number of neutrons, all we have to do is take the atomic mass and subtract the atomic number. Now you might be wondering why there's a decimal there. Well, the atomic mass takes into account all the versions of the element in our world. So these elements vary, so that's why this number is a decimal. And we'll go on to that in a bit. That's why we have something called isotopes. So elements of the same type, so all carbons have the same number of protons. But not all carbons have to have the same number of neutrons. In fact, they can have different numbers of neutrons. So for example, let's say we had carbon-12. That has 6 protons and 6 neutrons. If we had carbon-14, we know that it has to have the same number of protons, but this time it has 8 neutrons. That does not change what the atom is, that makes it an isotope, a different version of that element. And so going back, that is why our atomic mass has a decimal in it, because we might have more carbon-12 in our world than carbon-14, but carbon-14 has a different mass because it has more neutrons, so we have to take that into account. That's why sometimes we represent elements using something called isotope notation. We have X representing our element, A representing our atomic number, and Z representing the mass number, not the atomic number. So this time it's going to be a nice whole round number. So for example, for carbon, our element letter would be C. Our atomic number would be 6, and our mass number in this case would be 12. So that's how we would write something out in isotope notation. The last thing we have to talk about today are ions. So we know that atoms are normally neutrally charged. So the number of electrons plus the number of protons, because they both have a -1 and a +1 charge, they should cancel out to equal 0. But sometimes atoms will have a charge on them, and charged atoms will be called ions. So let's say we had a neutrally charged sodium, but we took away 1 electron. So we lost a negative particle. We got rid of something that was negative. So what happens to the sodium? It actually becomes sodium +1 because we lost something that was negative. But let's say we had chlorine and we added 1 negative electron, all right? And so we got more negative by 1, so we get Cl -1. And that's actually the basis of chemical bonding, because now we have a +1, a -1, and that makes NaCl, or table salt. But we'll go more on into chemical reactions later. All you have to know is what an ion is, and that is just a charged particle, or a charged atom. And that's all for atomic structure. So we've covered the subatomic particles, energy levels, isotopes, and ions.